Some people still prefer to use the table, but again, I have to warn you that College Board likes to do the thing where they give you everything but one thing and you have to solve for the one thing. So just, you should know about the formula. I seem to have lost my pen. I have a lot of pens. Ow. Oh, there it is. Okay. Sorry. Okay. Conditional probability. The probability that one event happens given, and this is the major clue here, this word given is the whole thing. Given another event has already happened. The probability that one event happens given another event has already happened. We're going to study this in 3 ways, like steak 3 ways. It's going to be a formula, a table, and on Monday, we're going to do tree diagrams. You probably haven't done a probability tree diagram since middle school. Some of them are spicy, some of them are annoying. Most of them are annoying. I don't love to draw them. That's just my problem. But okay, let's start with the formula. Okay, so first thing you need to know about this formula is that this means given. This vertical line that looks kind of like one side of an absolute value. This says the probability of A given B is the probability of A and B. So this is the and one. Remember, if you would like put a line here, it would make an A for and. So it's probability of one thing and the second thing over the probability of the second thing. Yes, Annie? The one that's given is the B. So A given B. You're dividing by the given. So what I like to think about it is you're reducing your options down to the given. It's like the given already happened, so that's all we look at. I still like to do it with a Post-it note, even though most of you are seniors. Still going to do it with a Post-it note. Okay. Example. This is the same table, by the way, that we used the other day. Given that, use both the table and the formula to find the probability of A given B. Interpret this value into context. Okay, so we're going to do it from the table first. Probability of A given B. Okay, so let's talk about what that means. That means the probability of being male given that you know they have a pierced ear. So you've got like, okay, just picture like a bunch of people in hoodies, faceless, but you can see their ears and you know they have pierced ears. What's the probability that they're male? All right. Okay. So what we do with my Post-it is we say, okay, we only want to look at the pierced ears. So this is where you start. I'm going to narrow my table down to the pierced ears, and you only look at that. Now that becomes the only thing you care about. And I'm going to shade this part. That is not my phone, by the way. That is a phone that a student left here that I'm hoping she'll remember at some point today, come back and get, so that I do not have to stalk her after school. That would be awesome. Okay, so I've shaded that part. That's the only part I'm looking at. Just looking at the shaded part, that's it. So I shaded the B. Yes, pierced ear. Okay, now what's the probability of both of those things? So 19 students have both male and pierced ear over total pierced ear. This over this. And we did this in chapter 1 when we made what's called conditional relative frequency table, and we're going to do that again in a minute. So this is 0.184. Do you have any questions about what I did? So you look at the second letter, figure out what that is. It's pierced ear. Block off everything but that, what you want over the total. Was that helpful? Okay. What? What? Okay. Look at the second letter, B. Figure out what that is. Pierced ear. Only look at pierced ear. Yes over the total. Okay, now we're going to do it with the formula. So that's a visual way for my visual people. Now we're going to do it with the formula for my formula people. Okay, reminding you that A is intersection, which is where they overlap. So this is saying, what's the probability that someone is male and has a pierced ear at the same time? That would be 19 over 178. Does that make sense to you guys? Okay, and then over the probability of B, which is just total pierced ear. So 103 over 178. Just wrote that wrong. And then, yeah, the denominators just cancel and you get 19 over 103, which is 0.184. Okay, we're going to interpret in context. Given a student has a pierced ear. You know, it's funny. Just reminded myself of how I used to teach people to use they, them pronouns. Like, I would say, imagine that, like, you walk up to somebody in a Target and they're just like in a hoodie and jeans and you can't tell what gender they are. And like, okay, what kind of shoes do they have on? What are they doing? Like, it's hard for people, not necessarily younger people. This was basically for my parents. But anyway, what? No, I was trying to teach my parents how to use they, them pronouns. So I was trying to get them to visualize somebody that was like in a hoodie that they couldn't see their gender and then describe them and they would use they, them to describe them. So it's like natural. Anyway, given a student has a pierced ear, the probability that they are male is 0.184. It's not. It's the phone that the girl left second period. Yeah. Okay, so the hardest part about this one is not going to be finding the probabilities. It's going to be using the proper notation and putting it in the right spot. So this is more of a translating issue first, and then the probability part will be easy. I promise. Okay. Do you guys need a minute still? Okay. Jamie. Or Olympic. We don't need this thinking help. If you get trapped in a classroom when everyone has allergies, it'd be best to be in here because we have Kleenex 4 days. Okay, anyway, are you ready? Given that a person is female, find the probability that the person does not have a pierced ear. Okay, this is going to be the hardest part. So, okay. What part of it is given? That they're female. Okay, and our notation doesn't have anything about being female. Yeah, so we have to call it not male. Okay, but since that's the given part, we have to put that second. Oh, struggle. Okay, so we're going to say given, not A. So you always want to do the given part first, but the given part is the second part in the parentheses after the given line. So this is given, not male. Find the probability that the person does not have a pierced ear. So pierced ear, not. Yeah, yeah, it's Friday though. Okay, now let's go up here to my table and let's do the Mrs. Talbot's, post-it note method. You want to narrow your table to this. So I only want to look at the not males. These are the not males. Does that make sense? Okay, so I'm going to take a different color. And down here, I'm just going to make a little like color swatch key to show that that's that part that I have shaded down to. Okay, and this part here says, what's the probability of not pierced ear? So how many students do not have a pierced ear? In the red section, 4. And how many total students in the red section? 88. Okay, now let's do it with the formula. Well, now that we know what's going on, this is sort of anticlimactic, but this is saying what's the probability of not having a pierced ear and not being male at the same time. So not pierced ear and not being male is this 4 out of 178. You could sort of cheat off of yourself from over here because you know the top has to be 4. And then probability of not being male would be 88 over 178. Cancel, cancel. We're not going to write the sentence again because I'm pretty sure you get how to do that. Any questions about like where all this business came from? No? Okay. As you're writing this, the thing I can tell that you're really excited about, uh, think about which one of the sides of the table is the explanatory and which side is the response. If you don't want to think about it like that, think about independent and dependent variable. Also, if you finish this and you're bored and waiting, there's a arts and crafts one for the very end that you could find in your packet and cut out. But we're not there yet, but if you're bored. Don't glue this in yet, by the way. We have one more thing to do after this part, and then we're going to glue it in. Did anybody figure out what the explanatory is? What would come first chronologically, gender or pierced ear? I mean, yeah, other than special cases, it would be gender first, then pierced ear. Okay, so what that does for us, it tells us which way to divide for our conditional relative frequency table. If you remember from chapter 1, that was a thing. So you had to figure out what the explanatory was. And if it was at the top of the table, you divided down. And if it was at the side, you divide it across. Do you remember? It's really old. No, we got nothing. Let me see if I can locate it. Oh, it's gonna be in, please hold. It's like, okay, here's the snowmobile thing from the summer. Remember the snowmobile thing? And then we did the dividing down. This is what we're gonna do right now. The dividing down. Okay. So there are 19 total males with a pierced ear over 90 total males. Do you see where I got these numbers from? Hello?
Yes.
Okay, are you sure? You see where I got the numbers from?
Yes.
There are 71 no pierced ear out of 90 total males for a total of 0.789. Okay, now question, did I have to do the second calculation really? Not really, because it has to add up to 100%. Okay. What would the numbers be here? Which is 955. And this one we already calculated was 4 over 88, which was 0.045. Okay, so the question you're asking yourself is looking across now at these two, are these equal? If these are equal, then it is independent. Means it doesn't matter if you're a male or female, whether or not you have a pierced ear. Does it seem to matter? Yeah, it definitely matters. How much more likely? Quite a lot, quite a bit more. Okay, but sort of spoiled my own next part of this lesson. So I really need to do the whole table. No. Didn't I get away with this being part of the day? When I get my answer just from this. Okay, so I need a formula for that now because we're just too lazy to make tables. I don't know about you, but I'm too lazy to make tables. I prefer to have a formula, but some people like the tables a lot. They're just visually oriented, which is great. Are you guys all done with this? You're fine. No, no, it's okay. I just want to plug in the numbers from our previous problem into this, and then we're putting it in. Okay, most of the time, this is a lot. I understand right here. This is right here. This is last year's notebook, by the way. That's this box. And this piece right here is this box. If you can show that those two are equal, then they're independent. We just did it in the table. I know, but what I'm saying is I don't want to make the table. I'm too lazy. If I can show that this equals just the plain probability of A, or this equals the plain probability of A, then that also means that they're independent. That's usually what you do. So this is what usually happens. The book gives you all of this. We're not going to use it all. We're just going to use, because I don't know what happened, but y'all have Friday brain. We're just going to use this bit and this bit right now. I'm going to see if this is equal to this. That's it. Okay, do we think we can handle seeing if this is equal to this? Okay. And then you're going to paste in the thing. Okay. Can you please look back in your notes and find me the fraction and the decimal for the probability of A given B? It's back in your notes. Scan back in there. Find it. Can you find it? Okay, what is it? Yeah, okay, so 19 over 103 is 0.184. You found that? Just okay? Okay. Now we're gonna see if that's the same thing as the probability of A. Okay, I'm gonna ask you a question. How many male students are there? Look at your table. 90. Can you tell that there's 90 male students? How many total students? Okay. is knowing that someone is male. Knowing that someone has a pierced ear and they are male, different from just being male. Yes. So that means they're not independent. They affect each other. Piercing that you having a pierced ear affects the probability of being male, changes it. Just male only is 50%. But knowing that somebody's male and having a pierced ear brings it all the way down to 18%. So these are not independent. So it's the same answer that we got from the probability table. Okay, last thing we're doing today is this, and it's not long, and it's mostly common sense. But there's a formula for common sense, apparently. And it's a little bit of a spoiler from Monday. You guys not have supplies. Sorry, I had to take them away from my fourth period class because they were ripping stuff apart, throwing it at each other. Junior boys, yeah. Let's see, given that you have trash all over your floor after a group leaves, what's the probability that this particular group of junior boys was sitting at the table? Pretty high, pretty high. And this is kind of humbling, to be honest with you. This problem has real data in it. So you've got all those friends that are like, I'm gonna go on to play in college. I'm gonna go on to play in college. This is the actual probability of that happening. So a little bit humbling. Consider this situation. About 55% of high school students participate in a sport. Roughly 6% of these athletes go on to play in an NCAA team. Use common sense and the general multiplication rule to determine the percentage of students who play a high school sport and go on to play an NCAA. Okay, so first, this is the and we're going to use the common sense first. So common sense. Like if I asked you to do this, like I could ask a 8th grader to answer this question. And they would not use the notation, but they would say, okay, probability of playing in high school and playing in college. So we're going to do the common sense. So 55% of kids play a high school sport and 6% of those play in college. This general multiplication rule is common sense. It just means that you say the word of. So 55% of students play a high school sport, and 6% of those. Do you guys see how this 6% is dependent on the 55%? Okay, and this comes out to be 0.033. So only 3%, 3 out of your 100 students will actually go on to play in college. Okay, we're going to take our common sense and write it into a formula. So you have the probability that something happens times the conditional probability of something else happens given the first thing happened. Okay, and we're actually going to do this visually also because this is what we'll do on Monday. We're almost done, I promise you. I'm sorry. I can tell you're all very unhappy with me. Okay, so this is high school. So you have a certain amount of kids play a sport, certain amount of kids don't play a sport. In this particular example, 55% play a sport. That means we can assume that 45% do not. Okay. Of those 55%, 6% go on to play in the NCAA. 94% do not go on to play in the NCAA. And the answer for high school and NCAA is 0.55 times 0.06, 0.033. So when you guys made tree diagrams in middle school, you didn't realize you were actually doing this particular section of AP Stats. This is just a regular probability, and these branches off of it are conditional probabilities because they depend on the fact that something else already happened. So I want you to think about that when you're doing the homework, and then Monday we're going to do tree diagrams, which will all have regular event happening and then something else depending on those events making our trees. Yep. Oh, I do have a joke. It's good. I think it's good. Let's see. We did conditional probabilities. Yep, yep. Okay, here's your joke. It's a Venn diagram about John Venn. Yeah. The Venn diagram, yeah. Because these were probabilities. So probability is what you want over the total. So what you want over the total for the top, and then what you want over the total for the bottom. But the totals end up being equal, so you can cancel them out.
But okay, so whether it's given or not, whether it's so that's not if, so everyone's data.
Yep.
So whether it has the probability of paying.
Yep. The probabilities have to be a fraction or decimal, right? So yeah, they can't be a whole number.
It's always going to be the total of each.
Yep.
Not a total of anything.
If you skip this part and you just use the table, you skip the totals part. So this part, oh yeah, only use the 4 and then the total there. This part cut to the chase. This part went to the formula, and then we cut to the chase. Like, it took another step to get there.
So if I was going to do like A and B,
Mhm.
so male and physiology is
19 over 178.
or 170. Okay, if I were to do A or B, it would be 19 over 170.
19 plus 84 plus 71 over 178. Because one or the other or both.
And is only one,
Yep. Or is 3.
or is three.